Well, hello everybody. Um, I'm excited to get started. This chapter is amazing, and let's get after it. What you're looking at is my son's. I know this bar stool sports or whatever. It's kind of cheeseball, but this guy Dave, and he's kind of loudmouth, but he likes pizza, and I love pizza. And we were in New York last Thanksgiving, not the year before, and we actually went to a place that he rated high, and it was really good. So, why do I bring up this young man? Because what we're talking about today, believe it or not, is that thing right there. This, a slice of pizza. We don't call it a slice of pizza in the world of mathematics. We call it a sector, and we don't call it arc length. In the real world, we call this a crust. But basically, your goal today is just if I give you a pizza, give you a slice, you should be able to tell me the area of that slice and the length of the crust. Okay? Sounds kind of weird, but uh, you can almost smell it. Almost smell it. This picture is kind of cool. If you're ever given a chance to go to the Olympics, you got to go. Okay? I know yeah, it's expensive, whatever. Well, it's this crazy conglomeration of people from all over the world, and it's just like so fun because everybody's there just to root everybody on. It's like 8 different countries around you, and everybody's screaming for the winner because you just know their heart and soul went for it. So um, I always remember this because I never understood why people, I kind of got it, but when I was little, I was like, why do they get a head start? And so this whole thing that we're going to find out today is, how much of a head start should you get if you're in the red track or the blue track? You know what I mean? For the distance it is. So it's kind of a cool little application. All right, let's get started. So here's perfect reason to do a video is here's a bunch of vocabulary. You just want to take a picture of it, make sure you know it, feel good about it. Remember, this is the sectors, the whole piece of pizza. We might call this the radius, the center, the circle. Chord is a line segment whose endpoints are on the circle. There's a very special chord called a diameter. A diameter is a chord that contains the center of the circle. This is something you'll only see in a kind of a pre-calculus book, but it's that weird part of the circle that is created by the circle and a chord, not the diameter. If it was the diameter, it would be called a semicircle because it would cut it exactly in half. But that is a segment. Cool. Um, we come down here, uh, yeah, maybe we do this chord and we cut this circle into 2 segments. Yeah, we don't just look at the small one and say that's the segment. We can say one's smaller and bigger, minor and major. And likewise, if I look at the arc, and be created between 2 points, and that's sometimes written as arc AB. When you are given 2 letters, you have to go to the shortest root, and that's called the arc AB, and sometimes called the minor arc, but it's traditionally that's the one. The major arc would be the longer way, and what you need to do to show that algebraically is you have to have a third point, and you're saying, hey, start at A, get to B, but take the path that contains that point. So if you're talking about a major arc, there's usually a third point that kind of says, hey, include me, include me. Uh, all right, and I like this picture because maybe you've seen these words before, maybe you haven't. I thought this is good. The difference between a secant and a chord is a line segment, and a secant is actually a line that intersects a circle in 2 points. Cool. A tangent is pretty cool. It intersects a circle at exactly 1 point. Exactly 1 point. All right. So a little bit of background. Man, I'm amazed every year. People know what pi is, 3.14, and some people can do it 100 decimals because they sat in a really boring math classroom with that poster up and just went like this every day. I'm surprised at how often that happens. But what this is saying in English is so important. So if you can interpret that in a sentence, then you understand it. All it's saying is the length around a circle, the circumference. That's what capital C is. Okay. If we take the diameter and we ask ourselves how many times does the diameter go into the circumference, or you could say how many times, let's say this is the diameter. How many times does that thing go around the circle? That's the same thing as dividing into it. So maybe we go 1, and then maybe 2, and then maybe 3, and there's just a little bit left. That's the 3.14 right there. 1, 2, 3, and a little bit more. All right. So we know that there are 3.14159. Oh, yep, yeah, maybe you heard that. And so on diameters that wrap around a circle. Okay. If we don't want to use diameters, we can use radiuses because there's 2 radius for every diameter. And it's never really written as 2r pi. For some reason, it's written 2 pi r. So the circumference is found by that. Very good. The area of a circle is pi r squared, and that's pretty cool. This is the radius. You know the radius. That's not as intuitive until you draw a really cool picture like I did, because I care about you. What is going on with this picture? All right, so you got 1,000, no, let's say you got about 15 people at your birthday party. You cut up this piece of pie, at each one of these pieces of pie, and so you're just kind of bored because they haven't shown up. So you take their pie and you've kind of stacked them. So you've taken this piece, put it right here, you've taken this piece, kind of reversed it like that. 37 more people come. So what happens there is we cut this up even into more pieces. Well, can you imagine what's going to happen to this? It's going to kind of, as the pieces get thinner and thinner and thinner, it's going to become closer and closer to an actual rectangle. And since that's the radius, we could kind of say the radius is that length. And then this is a bunch of the crusts, right? But it's exactly half the crust. Wait a minute, half the crust, the whole, remember the circumference is 2 pi r. So half of that would be pi r. And we all know that the area of a rectangle is length times width. So we have pi r times r, and that gives us pi r squared. Bamskis! That's what the area of a circle comes from. All right. So we're going to talk about 2 things, arc length and the area of a sector. The first thing is the arc length. They call it L. That's fine. Sometimes you'll see this written as uh, uh, the measure of arc length AB. And I just lied. The measure is actually an angle measure, so let's not go there right now. All right, so in the diagram, the arc length. So what's cool about this is you know about proportions already. You know about proportions already. So think about this with me. This length over this length, so the little piece over the whole thing, should be equal to this angle measure over the whole angle measure. That's it. It's a proportion. So check it out. The arc length L over the entire arc length, or the circumference, is equal to this angle over a full angle. This is new as of, well, today. That's the 360 degrees, but in radians, we'd say that's 2 pi radians. So you got to think of 2 pi now as a full circle. I know, it's kind of weird. Um, and then this angle is in radians. Angle theta in radians. I know it's written right above it, but that's typed and somebody else typed it. I wanted to write it. Well, then we just work it out. So L over the circumference, 2 pi r. We multiply both sides by 2 pi r. And look at that, the 2 pi's cancel. This cancels this, and we're left with a not very intuitive equation. It's like, what? All I have to do is measure the angle measure, if it's in radians, times the radius. That is remarkably simple. Remarkably simple. So you have to believe that the proportion is true. Little length over the whole length equals little angle over the whole angle. Once you start there, boom, you work it out and you get this formula. Okay? So please understand it comes from somewhere. You're not going to be asked to, start here every time. You start here every time. Okay? The arc length is equal to the angle times the radius. That's it. Oh, Mr. Sayers, what if we are given the angle in degrees? Well, instead of 2 pi, just use 360 in 2 pi. But notice at this stage right here, since we're using 360, not 2 pi, there's not a lot of cancellation. That's okay. We know the angle in degrees, and we put that, divided by 360, multiply by 2, multiply by pi, multiply by r, we got it. Same thing works. Okay, guess what? Nothing changes with the area of the sector. Nothing changes. So, oh, look at that. I covered it up with my hand like, oh, don't look, but you're looking. So the ratio is the same. It's going to be the area of the piece over the entire area. So there's your area of the sector over the total area is going to be equal to the same ratio of this angle over the whole angle. That's remarkable. So look at this. Look at how similar. That's why we put these two things together. Really works out well. We're going to use A for the area of the sector, not the circle. So sometimes I'll just write sector down there by the A just to make sure that I know I'm not dealing with the area of the whole circle. So area of the sector, pi r squared, we just proved that. Theta in radians, okay, measured in radians over 2 pi. That's what's telling us theta, this is theta, is in radians because we're using 2 pi. Okay, if we were in degrees and theta, the angle measure was in degrees, we'd have a 360. That's illustrated right here. All right, so we're going to multiply both sides by pi r squared. Not a lot cancels out. The pi's cancel. These, of course, cancel. So we're left with area equals, there's the 1/2 theta r squared. You have two equations to remember or write down or reference in your notes. Nice and neat. That's it. That's it. We're going to do two practice problems. We're going to call it good. So the sector has a radius 12 and an angle of 3 radians. Oh, okay. First thing I want you to notice is, are we working in radians or degrees? Okay. Find its arc length. So, sorry, I'm a fan of drawing a picture. It's 12. 3 radians. Remember, like 1 radian is about 57 degrees. So, if you want to keep it like kind of 3 radians is almost 3.14 radians, so I would say it's just less than a full half a circle. So that we'll say is 3 radians. I like to write 3 rads. I know in the book they use this crazy little degree sign or a little C. I don't even know. It's the only place I've ever seen it. So just write RAD, or if it's such a small number, it's kind of assumed to be in radians. Obviously, if there's pi used in it, then it's radians. So arc length is theta times r. Look at that. I have such great notes. Theta is 3. Radius is 12. So we get 36 centimeters. It really is that easy. I hate to say it. Isn't that beautiful? That's just beautiful. All right. For B, the area is equal to 1/2 theta r squared. Let's check that, make sure. 1/2 theta r squared. Good. So 0.5, theta is in radians, so we go for it. 312 squared. 144, 72, 216 square centimeters. Did that pretty fast. I think it's right. 144, half of 144 is 72. 3 times 70 is 210 plus 2, 6. I'm liking it. Not too tough. All right, find the area of the sector with the radius. So this is the exact same thing. So I will let you do that. Okay, you're back. I hope that went well. So the area is 1/2 theta r squared, 0.5 times theta. Oh, I don't know what theta is, darn it. And the radius, 8.2 squared. And the arc length, I just don't know what dang it. So maybe I should go here, L equals theta r squared. Arc length is 13.3. Theta, we still don't know, times 8.2. That's not squared, 8.2. Do you see how you're going to have to work backwards and forwards? You got two equations, so you're given the information. So here I'm going to get a number for theta, and I'm just going to plug that in, and we get I win. You got this. You're smart. You can do this. There's only two formulas. Your homework tonight is pretty obvious that you're going to get angle measures, you're going to get radiuses. Just work through those. That's pretty good. Um, nice little example here of one that doesn't quite give you you have to kind of work with both formulas. So I think we're okay with that. Um, Man, 4 and 5 are kind of the same. So here, look at that. They give you the arc length, they give you a radius, but they don't give you theta. I think you can, work just two equations, work backwards and forwards. Um, oh, look at this. Yeah, that's right. So in this problem, we actually did this problem in the Kahoot. It would be really cool to know this angle because that angle probably equals this angle, and therefore you could learn and figure out what that angle is. So maybe you remember this particular problem. Hopefully you do. This is probably the one thing, number 9. If we were in class, we would all cut this out of a piece of paper. So imagine taking point A and point B and sliding them together. That center is going to move on up, and it's going to create that cone. So I've drawn the blue outline here. Turns out to be the circumference of that. Okay, so maybe pay attention to what is R in terms of this picture. So be kind of cool. I don't know if I think I did ask you to do 10. If you have a tangent line, you know that that's going to be 90 degrees. That's a very important thing to pull from that. I would also point out this is the radius. Well, if that's the radius, isn't that the radius? So those little things to notice. 12, I would just draw a picture. Think about that sheep as far away from that post as possible and draw that kind of the shape and see if you can't figure that out for yourself. 13, some people just see it right away and some people will never get it for the rest of their life. So give 13 a shot. Don't spend your whole life on it. And oh my God, 15. There has got to be a better way than what I did. All right. I think I will give you my problem solving process. It's on the next couple slides. There's got to be a simpler way. And you guys are so smart. So this was a bugger for me. It took me like 7 steps. I found this, then I found that, then I found this. And they're just like, no. So good luck, everybody. Awesome to see you. Right at 20 minutes. Not too bad. We'll see you.